Okay, this part again is the subsequent part of the introductory vectors lecture that we finished up previously. Now we're going to deal with the decomposition of a vector. So that is extremely important, and I will highlight this importance via a multitude of examples. Let us consider the previous vector. The Cartesian coordinates. Of course, we have other coordinate systems with which I will cover in more advanced topics as a lecture herein. But for now, we're going to stick to the Cartesian system, and I have, again, my vector is, 2, 1, 2, 1, 2, 3. So my vector is this little guy here. So my vector C is 2 in the I plus 3 in the J. I don't know if you noticed I'm using a different marker. I think this is more adequate for a glassy surface, so we'll see. So what do we know about this vector? We know that, say, this is meters per second. This is speed, right? So what do we know about this vector? We know that it is going 2 meters per second along the x direction and 3 meters per second along the j direction. Do we also know something about this angle? From the previous, we said that yes, usually the way we handle this is going to be the inverse tangent of 3 over 2, right? 3 over 2. But can we also define, for instance, instead of this angle, what if we were to project? So what if we started backwards and say, well, now I have a vector, now I have this vector, which is the same, C, right? And I'm going to project this vector on the x-axis. So I'm going to have a so-called C sub x, which we know for a fact it is 2, right? We know that the magnitude of my x direction is 2 meters per second. Now, how would I define this C sub x, this part that we highlighted? When you decompose the vector on the x-axis, you have the C sub x, which is no longer a vector because we know its direction, right? We can sort of call it as a scalar in terms of magnitude, right? So what is that? Would you agree that this is essentially C, the vector C, the magnitude of the vector C times the cosine of the angle phi? Well, let's see why. Cosine of this angle is defined as what? C sub x divided by the hypotenuse, right? Which is, well, exactly this. The cosine phi is defined as C sub x divided by the magnitude of my vector. Look at this. That is precisely the very definition of cosine. And at the same time, if you were to decompose this into the C sub y component, you would write the exact same thing, meaning your C sub y, it would be the magnitude of your vector C, which we found earlier, and we're going to run a few calculations times what? The sine phi. Let's see why. The sine phi is opposite this guy, which means this guy, divided by the hypotenuse. Again, you can see that very easily that C of the angle phi is C sub y divided by the magnitude C. Let's run a couple of calculations and see what we come up with. It's going to be pretty interesting, I promise you. So let's take this. We know that this must be equal to 2, right? The magnitude along the x direction, we know it's 2 meters per second. We know that this, from the previous calculation, we found the magnitude of C. I think it was about 3.6? Yes, 3.6. About 3.6, we took the square root. That was found as 2 squared plus 3 squared. I remind you, and I remind myself, 3.6 We know the angle. We found the angle as 56 from before, right? We found the angle as 56.3 degrees. And let's, plug all the numbers here, and we're going to have, what is that, 3.6 times we find the cosine of 56.3 in degrees, and that comes out to be 0.55. And if you do this calculation, you will not find exactly 2, but you're going to find something very, very close to 2. And now you're going to say, well, why is it not equal to 2? I'll tell you why. Because the moment you take the sine, the moment you calculate an angle in degrees, it is so sensitive, the calculation is so sensitive that will never yield back number 2 exactly. Right? So we have lost some significant digits calculating the cosine, but we have also lost some significant digits from taking the square root, because they're both irrational numbers. But algebraically, you can always say that I can decompose my vector into my x and y axis using the cosines and the sines respectively. And that is a very, very important practice that we have to do, especially when we're dealing with free body diagrams. And again, I will show you examples. That are occurring, and you will encounter very, very frequently in undergraduate physics, and that will be in the next couple of videos.